Yes, good morning, everybody, and it's really a pleasure to see all of you here. It is a bit of a special moment for me to talk in front of so many people that I have, read their things from for all of these years, and so and also, this is just as a disclaimer, I'm jet lagged, so please, bear with me. But yes, I'm going to talk about analytical data management with DuckDB. I'm very excited that I get to speak at the No Bullshit Data Conference, because that's also very much our credo. So I'll promise you not a single mention of AI over the next 45 minutes. Promise. A little bit about myself. I've been doing SQL for a long time. This is actually my license plate from my very first car. This is what it looked like. It was a lot more rusty than that. This is a good picture from somebody else's car. But I want to start with giving you a bit of the backstory of DuckDB, because I think it's important to get some idea of how this all came together, because I think it is very much an idea born not in a vacuum, but in sort of a kind of, now it seems obvious, but in an environment that kind of facilitated it. Okay, so I'll start with the backstory. Cast your mind, everybody, back to the ancient times of 2015. Okay? In 2015, the most popular song was Uptown Funk, and the most popular movie was Star Wars: The Force Awakens. I looked this up. It was also the year that we get the Iran nuclear deal, so that was a good year, I think. But what happened in data in 2015? So I basically made a Matt Turk slide to give you some overview of what happened, especially in analytics. Okay, we're going to go through these things, and we're going to talk about how this created kind of the breeding ground for DuckDB. So if you wanted to analyze data in 2015, you had a choice. You could go for the enterprise special at the top left, which basically meant that you had to hand all your money over to one of these companies called Teradata or Vertica or Greenplum, and they would have super secret, super sauce, that would make your OLAP queries run fast-ish. Okay, if you didn't have so much money, you could go to Hadoopistan, which was still a thing back then, where you would run on wonderful tools like Hive or Impala, and actually Spark just started, I think, the year before, so it wasn't really there. So that was choice B. I don't know, not ideal either. Then we had the cloud toddlers. They're called cloud toddlers because at the time, BigQuery had just launched. It was a small thing, not in like this massive behemoth that it is now, and Redshift has also just launched. So it was also not really something that you could go to. And then you had, of course, the add-ons to dinosaurs. So I'm sorry, but it's true. Where every single DB vendor out there added some columnar capability to their 50-year-old system. And I did look this up. This was all happening in the same time around 2015. So it wasn't really great. And me, as a then academic of data systems, was a bit frustrating, right? Because we knew there were these obscure academic spin-offs like Vectorized from Amsterdam and Hyper from Munich that had a far superior technology, right? Like we're talking about vectorized query execution, we're talking about jitting queries, but they were not accessible. They were hidden in these obscure things that got sold and then swallowed up by sort of corporate overlords and never saw the light of day again. Not great. And then we have the despair engineering. That's also something that I wanted to talk about, is where people, out of despair with the state of analytics, build an entire sort of new tool chain, right? So for example, we have one example I think is really nice, is data table, which is a really impressive piece of engineering for our data frame specifically. That was there, in my opinion, mainly because there was nothing else. I think part of the origin story of Pandas, Wes is here, so he can tell us more about this, also came from this sort of despair. And I'm sure you can relate to GNU parallel level of despair of data processing, right? I mean, it is the thing that you reach for when you have no more options. But that was the state of things. So let's meet our protagonists. So it's me, and on the other side is Mark. In around 2015, we looked at this and we decided that this is just offensive, right? It cannot be that this slide is the state of things for working with data when we know that better options exist. So this is our train of thought here, despite engineering. Yeah, so it's a new term. We invented it. Okay, so here's this train of thought roughly. We can't just pip import the state of the art in data. We might have to build this ourselves. But then we talked to people who had done this sort of thing before, and they said, well, this is nice. You can need 100 people for 10 years and like roughly many millions. And then we are like, oh, that's not great. We don't have many million. So what now? But then we observed a sort of really like glitch in the matrix, a supernova at the other end of data processing, which is SQLite, which also became really popular in 2015, where somebody, one person, so not 100 people, 10 years, but one person, at that point I think 8 years, built kind of the status quo in how people manage data on everything, from the browser to phones to everything out there, with a focus on transactions. So that means like storing a row, updating a row, things like that. So then it became clear, and it's a very fitting slide in this place. Didn't know about this, that we needed to build the SQLite for analytics. That was obvious. It was something that was tractable. It was something that could really make a change in the way people were looking at data, given the sad sort of state of the world around it. And sort of that's how this all came about. I think it's a prime example, as I said, of spite engineering. But so be it. All right. So you want to build a new database. It's an experience that is kind of an interesting thing, right? Because people tell you not to do it. And I, standing here, will also tell you not to do it. Because that will be positive for our market share, obviously. But no, I'm telling you not to do it because it is a risky undertaking. We were only able to start building a new database because we were basically an academic research institute at CWI in Amsterdam. Our salaries were kind of dealt with. We could basically take a risk. I had gotten tenure, Mark had finished his PhD. There was there was space. But once you start deciding, and there was I remember the night after many beers, we decided we'll do it. You have a lot of design decisions because the data space, as you all know, is vast. There's lots of things you can do or not do. So I'll try to walk you through some of these design decisions and try to explain the rationale behind them. The first one and the biggest elephant in the room is distributed. Okay? To illustrate distributed systems at their peak, I have a picture of the original Google data center here, which I call cardboard-based engineering because they had to put the cardboard between the main boards and the racks to stop them from shortening out. And they just used the cardboard that the boxes came in, as far as I know. So the biggest question in 2015, and maybe also today, is does your system need to run in a distributed way? Well, this is a great question. There are some people that have kind of pointed out some problems with this. There is an interesting paper, has everybody seen it, from Frank McSherry, who also gave a talk here at Data Council about this, actually, in 2015, I think, or 16. Basically, this paper shows that any sort of competent single-thread implementation is going to be better than the state-of-the-art of distributed systems. And this is the general problem of distributed things. They are so much harder. And we experience this whenever we try to teach a course about big data with students that couldn't, get stuff running. It was an absolute nightmare. The cost of running distributed things is just massive. And it's the cost on the person, it's a toll on everything. And meanwhile, what has happened is that also we have now seen this, but at the time it was an assumption. This is a slide from George Fraser. I don't know if he's here, but he's going to be here today, I think, showing the amount of data that the fraction of the queries is scanning, and it basically shows that the median query runs like on 100 megabytes of data and the P99.9 on less than 300 gigabytes of data. And hardware had grown so much, like a single MacBook is easily able to handle these kind of things. So we went with DuckDB, we went for single node, and that was a design decision that I'm still happy with, but it I thought this is for sure going to be ridiculed till the end of time, right? The fact that I'm standing here makes me happy because it means that I'm not going to be ridiculed to the end of time, I hope. But it is I think the biggest departure from the common wisdom at the time. I think it is still the biggest departure of the common wisdom now, even though we have seen all these things about data sizes being not as big. You know, Jordan has talked about this. We have seen all these things about how hardware capabilities are growing faster than compute, than the data sizes, I mean. But this is the biggest design decision, I think, that we made that we're still kind of proud of. I'll walk you through some more design decisions, okay? I also have been told that Drake is no longer cool, so I've picked an alternative, okay? The next question is, if you want to build a data engine, is like, what execution paradigm am I going to use, right? Obviously, you make an analytics engine, so you can either go for Amsterdam-style vectorization, or you can go for Munich-style JITting. Obviously, we were from Amsterdam, so we had to pick vectorization. It's not true. The reason we picked vectorization for DuckDB was because we needed something that behaved like SQLite, that was small, that was lightweight, that was easy to put anywhere. Research has shown, you know, performance-wise, these things are kind of comparable for analytics at least. And we needed, as I said, we needed something we could ship in a small package, so vectorized is. And again, we haven't really looked back on that. Then, you know, this comes up, I think this question I get like once a week or something like that. When will you finally make GPU capabilities for DuckDB, right? And the answer is never. Because in my opinion, there's absolutely no point of making data transformations run on GPUs. But beyond that, if you're trying to be a SQLite sort of level thing that can be run anywhere, you cannot start linking to these GPU frameworks. You just can't, right? Like the amount of drivers nonsense that has to happen, the amount of operating system pseudo access that you have to get anything of this working. It's insane. So CPU it is, and I still think that it was the right call. Another thing this is a bit more, goes a bit more into detail. Another thing that the common wisdom told us that we needed in order to get good performance on the CPU. We picked the CPU, so now we need to get good performance CPU. And the common wisdom told us that the only way of doing this is to write explicit SIMD code. So basically, these are special instructions that operate on multiple data items at a time. But the thing is, if you do that, again, your portability goes out of the window because now you've basically hard-coded your database kernel onto, let's say, an Intel platform. And not only any Intel platform, but like the AVX512 platform with the dash something. That is really going to be a problem when you want to try this to run this on everything else. And so in DuckDB, we said, no, we're not going to do any hardware-specific code. We're going to run scalar code, which is shockingly easy for compilers to then turn into SIMD code behind the scenes, but that's a different point. We went for scalar code that can run anywhere, and this has been really amazing when halfway through the development process, it was clear that ARM were going to win, and we had to sort of switch CPUs. And it took me a grand total of 5 minutes to get DuckDB running on the M1 when it came out, which I think is unheard of in the sort of serious analytical data engine space. If you had a JIT engine, you would still be working on rewriting your JIT. Some people here are clearly working on that. Sorry. And then the final thing on these like yes and no slides that I have is the licensing choice. Obviously, we had seen how really amazing systems disappeared in corporate sort of hellholes. And SQLite being a shining example of being actually in the public domain, which is amazing, has shown that in order to actually make an impact and to change the way we think about wrangling data sets, we needed to be open source in the public domain. So all of this put together and many other design decisions end up with DuckDB, right? So I have a question. Who here has used DuckDB? It's my kind of crowd. So yeah, get a record. Okay, so I don't have to tell you what DuckDB is. It is in like a long amount of time, but it basically is we call it a universal data wrangling tool because people get scared when they hear SQL. It's a universal data wrangling tool. It is the SQLite for analytics. We're still very happy with that moniker. And it is actually the fastest growing database management system to date, according to DB Engines, which I think is something that we're really proud of. So this is the point in the slide deck where you expect me to show impressive benchmark results, yes? Yes. Is that true? Okay. So these usually look like this, right? Somebody makes a plot and says our system, their system, and it says fast here and slow up there. We actually wrote a paper about how stupid benchmarks are. It's not saying DuckDB doesn't do well on benchmarks. It's just that it is quite difficult to make a credible benchmark, which is why we at DuckDB we like to compare ourselves with past us, right? Which is also generally a sane thing for humans. Compare yourself with past you. So we try to do the same. That being said, there's one thing I wanted to show you because it made me laugh, or made actually the whole team laugh a couple of weeks ago. So who has seen this, by the way? Yeah, a couple of people have seen it. So this is a website for so-called the real-time analytics benchmark, right? And so if you click on the website, this is what it looks like. And you see, it looks a bit like ClickBench from ClickHouse, which DuckDB is also doing quite well on. You look at this website and you see, okay, well, system and machine timescale seems to be doing well. If you click this button, however, this little batch analytics button up there, if you click that, then shockingly, suddenly DuckDB is the fastest. And we thought, that's kind of funny. And we thought, why on earth did I do this? But they thankfully said in their blog post why they excluded it. And they said, well, DuckDB isn't built for real-time analytics, so it's excluded from the results, but was the fastest. I mean, at that point, we have to get the strategic popcorn reserves out at the office. It's like, anyways, anyways, it's surprised it's faster than timescale to be there. Just as a tip, if you're making the benchmark, this is embarrassing. Probably you should change the benchmark until your system is the fastest. But anyways, this is why we don't do benchmarks, because people make fun of you. Anyways. DuckDB is popular, which is wonderful to see. It's quite humbling, actually. There's this, the VC happy graph. The number that I'm more interested in is actually, that I'm more watching, is the amount of unique visitors to our website. And we've accidentally made one of the more popular websites of our country, the Netherlands. So we've beaten several large websites already just from people looking at our documentation, which is wild. Yeah. We eventually spun off DuckDB from the CWI, the research institute that it originally was developed into a company called DuckDB Labs that basically employs me and Mark, the original creators, and also a bunch of other people that we collected over time, and it's now a small company, and I'm happy to say it's going well. The company sells support and consulting services around DuckDB, but it is actually bootstrapped. A lifestyle company, as VCs like to say, and it doesn't have to make money. It has to sort of sustain the team. The project itself is actually in a non-profit foundation that holds all the IP, a bit like Python, and it's really I think it's an interesting model that we kind of were able to take this software and keep developing it with a team of more than 20 people at this point without having to get any investment. All right. So now, finally, I was asked to go deep, so I will go deep. I will show you some of the most recent work we're working on DuckDB, since you all like DuckDB, clearly, because you've already used it. Maybe you had to, I don't know. I'm going to show you something that we're really excited about that we've been working on for years, which is dealing with not enough memory. Okay? So traditionally, the world looks like this in data management systems, and especially analytical ones. This plot takes a bit to unpack, so I'll take my sweet time. We have, on one side, we have the execution time is our axis, right? Our y-axis. And on the x-axis, we have the data size. And what you would expect to see, and what you often see, I mean, not in all queries, but for many of them, you see as you crank up the data size, your execution time goes up, In this case, it's log, but it goes up, right? If you double the data size, you probably should double the execution time. That seems fairly reasonable, right? Okay. But then there's this interesting thing that happens at this dashed line, which is the memory limit, where many existing systems do two different things. One, they start jumping, having this huge performance cliff, where basically they switch to a different implementation, and it's becoming super slow after this. For example, Hyper, which is in Tableau, which is part of Salesforce, they do this. And the other option that's also used by quite a lot of systems out there is just crash. It's not great. So we have been working super hard on like looking a bit more like the blue line, right? Like somehow keeping going. And the latest thing we've been working on there is this paper. It's called Saving Private Hash Join, together with Laurens, who is working with us, and Paul and Peter from the Liberating. And Peter, you may have heard of Peter. He's one of the I would say one of the famous people in databases. And so we've been working with this. I'll just show you a bit the notion of how this works, to just show you how we try to kind of make sure that the query is always complete, given that there's hardware resources to do so. So here is the first thing that I think is super interesting about this paper. In operators like the hash join, or also in sorts or in aggregates, one thing is that you have to understand is that even if you have a columnar vectorized system, your data needs to be in a row layout, which is really counterintuitive, right? You go from a columnar, everything is better in columnar, you ask the dinosaurs, to a row representation. It has to do with, complicated hardware reasons of like locality. In things like joins, you look at the data kind of in a row-wise sort of fashion. But then we have this annoying thing that people have data with like that has like strings in it. It's getting really in the way of efficiency. People stop having strings everywhere. And not only do people have strings, they have variable length strings. I mean, what are you thinking? To fix this, we have this layout where we have these row pages here. These are like, for example, the orange one top left here, that is holding the row data like integers and things like that. But then we have these annoying strings that we put into these variable pages that are on the right, because there needs to be an indirection because the strings have funky lengths. But the tricky thing is now, in order to basically make queries work with an arbitrary amount of memory, we have to be able to move these pages out of RAM and back into RAM. And we ideally do not want to punish the case where it does fit in RAM. So this is this special layout that we came up with, where we have pointers in these pages, but we store a base pointer, so we know when we look at these pages again after doing other things, we know whether they were swapped out or not. And this allows us to basically go over memory, the memory limit with operators, and still have a fast case when stuff fits. So this is one ingredient. And the other ingredient is like extremely diligent and annoying work on a single operator. So here's the join operator. This is the first. Get ready for a lot of builds in this, okay? You ready? Okay. So we start on the very left with something called morsels. This is because of the parallelism model that DuckDB uses, called morsel-driven parallelism. It came out of Munich, where we do not partition the data before we read it into the operator. Like in the olden days, we had volcano-style parallelism, where the operators were unaware of parallelism, but then you would have these exchange on partition operators to make sure that the semantics worked out. In morsel-driven parallelism, you just take a chunk of input and you assign it to a thread and you're happy. So basically we get this input and we have these different colors in the input on morsel 1, 2, and so on, mean that we have rows that are for the same join key in any of these inputs. We don't know where they are, right? So what we do now, we start partitioning. We start partitioning for each thread, which means the threads can run independently at full speed, running through the input, partitioning the input into hash partitions, and also materializing in the row format that I just described, right? So we take the input from columns and take it into this row format. This is shown in the picture by going from the little column to the little row. Okay, so now we have all the orange things in one partition in rows, and but we have several places between these threads, right? Now we do an exchange where obviously we have to put all the orange things together and all the blue things together and so on. And this is, by the way, one thing where being in a single node is really nice, okay? Because it means that you don't have to start talking to 1,000 servers when you do that, right? It's like you move some pointers around, right? It doesn't even get copied. So now we have these pages in these for each partition. It's radix partitions. We have a bunch of pages that contain these rows in row format. And so that was our build phase of our hash join, right? So now we have the build side where we prepare for the actual join. We have finished. So far, so good. And now the sort of the amazing thing that of this concept starts. So that we start now probing the other side of the join. And here is normally where the previous systems would have to either go to an external sort merge join or crash. Because now we actually do not put the entire hash table into RAM if we don't have the space. We pick some partitions. In this case, we pick 2 of the partitions, the blue one and the orange one, to build a hash table on, and we can pick that based on the amount of RAM we have, right? By the way, in the previous page, these things now, if we run out of RAM anywhere at this point, these can go out of RAM. So, but it doesn't matter. Now in the probe, we can pick some of the partitions and then start probing them and produce output. And if the hash tables connected with all partitions fit in RAM, all is great. You know, basically it's super fast, nothing bad happens. But here's now the cool bit. Anything that we didn't manage to put in RAM, and from the hash table perspective, for here the blue things, we put into this overflow. So we actually put this on in another sort of buffer. Again, it can go out of memory, and that means that we scan this into this overflow. And once we're done scanning the input, we basically start scanning the overflow buckets, and we can basically say, okay, now we scan the overflow, and we need the green partition for the hash table. Now we pull that back into memory, and we can continue. And we continue that essentially until we're done. And this is the end-to-end flow chart. I wanted to show this because it kind of shows the amount of engineering that is required to make something like a hash join work on arbitrary memory sizes. But it's the kind of thing that we do because we really believe that a system that people rely on should never say, oh, I cannot finish this because I don't have enough memory to do this. But at the same time, we still want to use memory. We want to use all the memory we can because it makes it faster. So this is this is kind of the ongoing work on operators to show, to basically improve the larger memory performance of DuckDB. And here's the benchmark. I lied when I did say I didn't do benchmarks. But for scientific papers, you actually have to. They don't let you get away without it. So here's a benchmark against Postgres. Of course, the poor Postgres always gets beaten. And then we have Hyper and Umbra, which are systems from Munich, which with whom we have sort of a sporty relationship. His system does better. And here we show, and A basically means abort, and T means timeout. Okay, you can see that Hyper has this interesting step behavior. You see this in the upper plot, where it will switch to another algorithm and then always continue. It's wonderful, but it's quite slow. Postgres will just time out. Umbra doesn't have out-of-core capability, so it will just crash. And DuckDB has this like nice line that basically means that we can continue to run joins. This is this principle we call the never give up, never surrender principle. For those of you who like Galaxy Quest. Okay. So, but let me back up a little bit. So we've went deep on an operator, but the title of the talk said Liberate Data Management. And what do I mean by that? And here's a slide to show that. So this is the main thing that has changed, I think, with DuckDB being around, is that our architectural sort of convictions has to change. We used to have a two-tier architecture where you have your data system, you have your clients. We had a three-tier architecture with the data system, application server, clients. You had like lakes and lambdas and all this stuff. But the reason DuckDB, I mean, because DuckDB is the SQLite for analytics, you can put it anywhere, and people do. So these are all real-world examples, actually. So for example, on the very left top, right, people run DuckDB on their operational databases, not to run their operational databases. Please don't run transactional databases on DuckDB. They'll use something else for that. But then you can use DuckDB to basically pull, for example, out of your Postgres server, pull the data and put them into data lake. You can use DuckDB in lambdas, right? Like, there's no need to stand up a database cluster next to your storage cluster. You can just run that thing right there, for example. Application servers is another example. We used to sort of be so used, we were so used to the fact that we scale the application server and the database server differently. There are different things. I'm sorry. But now you can just run DuckDB on the application server, not a problem at all. But I think the biggest revolution we saw was putting DuckDB on the client. So people can run DuckDB on like laptops, on phones. People run DuckDB on cars. People run DuckDB in outer space. People run DuckDB in web browsers. And that's really something that amazes me. So just this morning I saw this, where somebody built a SQL-powered Doom clone in the web browser using DuckDB. In case you want to look at this, there's the URL. But this is absolutely mind-blowing, right? Like, the kind of things you can do in the web browser now is just entirely insane. And you can move your data pipeline entirely in the browser. People do. It's nice. And I've mentioned that I don't like benchmarks, but I do like performance, okay? But performance on a sort of a fixed size data set is really not nice. It doesn't really change anything. It doesn't really enable users to do anything they weren't able to do before. Here's something that we've been working on recently. We've been trying to see how far we can push DuckDB on different hardware. And we start with a Raspberry Pi, 16 gigabytes of RAM. And we've been able, without any sort of hard lifting or anything, it's just not like 10 scientists in white coats trying to hand massage this Raspberry Pi. And I just run it. Managed to run the TPCH scale factor 1000 on this thing, no problem. Then you go further. You take this laptop here, MacBook Pro, standard laptop. Everybody has one. Maybe you don't. Maybe you have less RAM than me, but you can run scale factor 10,000. It's completely insane, right? Like, you can just run that benchmark on this thing. And just last week, Gabor, our wonderful DevRel, he has managed to run the scale factor 100,000 on a single node, an Amazon box with 1.5 terabytes of RAM. Totally insane, right? Like, going back to this, we need to have distribution to run these kind of data sizes. Kind of makes it kind of, I would say, somewhat less relevant, maybe. Okay, so that's almost it. I would claim that we have kind of finished the sort of the single-player campaign of DuckDB. Yeah, is that fair to say? Like, this whole thing we set out to do is make data management, like, on a single computer work well. I think from that perspective, we can say we've gotten pretty close. So we pushed it sort of as far as possible, as ducking possible, which is why I'm really excited to kind of tease one thing here. Here's the logo of something new we're working on. I'm not telling you yet what the name is, but in 3 weeks, we're going to show the next sort of level of DuckDB to the world. I'm really excited about that, so stay tuned. So now I'm really happy to take your questions. Thank you.